This is question 5 of the spring 2025 midterm. So here we have a cryptography question. We have a few formulas describing a encryption scheme called AES combo, and they're defined here. And the first part is to select the correct encryption formula for I is greater than or equal to 3. So for questions like these, I think it's a lot easier to think about them once we've defined all of the decryption formulas. So let's just do it for all the values of I instead of just I is greater than or equal to 3. So first we can find the encryption value for P of 1. And we know that it's just decrypting C1. By decrypting C1, we get the inside of this encryption sort of thing, which is IV1 XORed with P1. And so we can just XOR this with IV1, and that should give us P1. And we can do the same with C2. So the first thing to note is that even before encrypting this, we're going to need to XOR it with C1. So C1 XORed with C2, and then we can decrypt this. So let's just put that inside the decryption. And then what this will give us is the inside of this encryption thing, and then we can just XOR it with the IV again, IV2. And then now we have the general formula for all values of I greater than or equal to 3, which is going to be the answer to the first part. So let's just do that. P of I equals to the decryption of C of I, which will give us the inside. So that's inside over here. And we're just going to need to XOR it with C of I minus 2. So that is our decryption formulas for all values of I. And so for the first part, we just want the one that it's I is greater than or equal to 3, which is just the third part over here, which would be answer choice D. Cool. So we can move on to the second part now. Select all methods for generating IV1 and IV2 that result in AES combo being IND CPA secure. So remember that IND CPA secure is a sort of standard for encryption algorithms. And so we can go through these choices one by one and see which ones are IND CPA secure. So the first choice is where IV1 and IV2 are independently randomly generated. So by looking at the encryption formulas, we can see that this I minus 2 creates some interesting behavior. What it happens is that all odd values of I are sort of an independent entity from all even values of I. And what that really means is that we have sort of two sort of chains going on. And because these two chains sort of simulate a existing sort of encryption scheme, which is AES CBC, we can say that these two chains that are independent are both IND CPA secure, so the whole thing is. And so answer choice A is correct. The second one is we seed a pseudorandom number generator with our key K and set IV1 and IV2 as outputs from this random number generator. The problem with this is that the output of this is deterministic because we're seeding this pseudorandom number generator with K. And because IND CPA schemes cannot be deterministic, this answer choice is not correct. So we can move on to answer choice C, which is very similar to answer choice B, where we're seeding two separate pseudorandom number generators with K, and we set IV1 equals the output of the first generator and IV2 as the output of the second generator. As we can see, the problem with this is that IV1 and IV2 are going to be equivalent because the pseudorandom number generators are seeded with the same key. What that means is that we can sort of simulate this IND CPA game, basically considering the fact that the IV1 and IV2 are the same thing. And what we can note is that C1 and C2 are extremely similar, And if IV1 and IV2 are the same, then the only thing distinguishing it is the XOR with C1. And so what we can sort of do is create a message where P1 and P2 are the same, making these two chunks exactly equivalent. And then the only difference is that C2 is the XOR of C1. And so what that means is that we should expect C2 to be all zeros, because something XORed with itself causes a string of just all zeros. And so we'd be able to really easily identify that exact string. And so the scheme is not in CPA secure. The next two answer choices are very similar, D and E, where IV1 or IV2 are randomly generated, and then the other one is the hash of the first one. And so remember that hash functions output a pseudo-random and unpredictable value, which means that by hashing IV1 in answer choice D, we are effectively creating another pseudo-random string of bits. And so it should be almost equivalent to option choice A, computationally equivalent to option A, which means that both D and E are in CPA secure. And so we can move on to the next part. So it says for the next two subparts, we suppose a ciphertext C gets modified in transit. And the way it gets modified is described in each subpart. So we want to let P prime represent the plain text from decrypting C prime, so the modified ciphertext. For each row, we want to select the corresponding value, and note that garbage refers to a pseudo-random string. In other words, something that we can't really interpret after it's decrypted by the block cipher, basically garbage. So the first part is that C is modified such that the first part of C is XORed. So the last bit is XORed. So looking back at our decryption algorithms, we can see that the only values that are being affected by C1 being modified is P1, P2, and then P of I equals 3, because that way we get a 3 minus 2 here, which is C of 1. So we expect P of 1, P of 2, and P of 3 to be affected by this change. And when it's being affected, it goes through the decryption algorithm, and because even though only one bit was modified, the decryption algorithm will output something very, very different from the expected value. In other words, garbage. And so P of 1 prime, P of 2 prime, and P of 3 prime are expected to be garbage. P of 3 prime is not here. And then everything else should be the same behavior. And so these two choices at the end should just be the same. Note that because we're only modifying the first ciphertext block, this result does not chain down to, like, for example, C3 or C5 or C7, because C3, the value of C3 is unaffected. Or sorry, the value of C5 is unaffected, because that only depends on C3, and C3 itself is not affected, but P3 is affected. Let's move on to the next part. Very similar, but now we're modifying the second block of C. And so we can sort of look at the encryption or the decryption algorithms again. We can see that P1 does not depend on C2, and so P1 should be expected. We should expect to have the same behavior as before. P2 does depend on C2, so we expect P2 to be garbage. We can also say that P4 will be affected by this change because that one also depends on C2. But also note that P6 does not depend on C2, it depends on C4, and C4 is unaffected. So going back here, we can circle the answer choices. So P1 is unaffected, P2 is affected, and it would just be garbage. And then all of the other ones are unaffected. Let's move on to the last two parts. So for this part, we're assuming that IV1 and IV2 are equivalent, and we're setting it as some value called IV. And this IV is randomly generated. So we want to provide a strategy that wins the end CPA game for this scheme. And here it kind of describes what the end CPA game is again. Basically, we get to choose 2 different challenge messages, and then the challenger will choose one at random, give us the encryption of that message, and then we want to guess which of the 2 messages we sent was encrypted. So in this strategy, we don't actually get the option to choose to query the challenger beforehand. And so the first part of this is there's a second challenge message, or one of the 2 challenge messages, and prime has been decided for us, and it is 2 randomly generated blocks. We can only set the value for m. And note that both m and m prime are 2 blocks long. So what value of m will allow us to determine whether or not m or m prime have been decided? So if we look back at the encryption algorithms, specifically what I discussed earlier when I was talking about 5.2, when IV1 and IV2 are equivalent, then these 2 sort of encryption blocks look very, very similar. And in fact, if we set P1 and P2 to be the same, then these 2 encryption blocks are identical, except for that C2 is getting XORed with C1. And because C1 is equal to this, and we're XORing that value with the same thing, we would expect C2 to be all zeros. Remember that some value X XORed with itself is always going to be just zeros. And so here, if we set P1 and P2 to be the same value, we would expect C2 to always be all zeros, no matter the value we choose. And that is an extremely sort of revealing fact for that message, because it allows us to really easily identify which message is being sent. If we set M1 and M2 to be equivalent here, and the output of the challenger includes all zeros as the second cipher block, then we know that our message M was chosen and that M prime was not chosen. And so that is the strategy that we can do here. So the 2 messages M1 and M2 must be the same, or parts of the message. And then the strategy would be that if C2 equals to zeros, then guess M. Otherwise, guess M prime. And this should give us a very high chance of guessing the correct message, significantly greater than 50%. And that is all of question 5 for the midterm for spring 2025. Thank you.